So our next speaker is Ankur Moitra. And Ankur is a professor at MIT and just a wonderful theoretical computer scientist overall.
Thank you. So today I'm going to be talking about model stealing for any low-ranked language model. So let me give you some background and motivation, since I don't usually work on language models. Let me tell you about this unfortunate fact that we all have to deal with, which is that a lot of our favorite language models that are out there are their inner workings are kept as trade secrets, right? So a lot of details about the precise structure of their architecture, what kinds of resources went into fitting those models, how the data set was constructed and curated and cleaned, and a lot of details about the training methodology are all kept secret, right? But there's this funny thing, which is that you still are allowed API access to these models. So if you're a subscriber, then you can issue queries to the model. And one of the questions I'd like to explore in this talk is, if you're allowed API access to a model, in what sense does it change how you think about the security? So is it possible that through query access to the model that you can actually learn important things about the model you're interacting with? Can you learn about its parameters? Can you learn aspects of its training data? And you can, reverse engineer some parts of that. Or can you duplicate aspects of their functionality? So, just to be concrete about this, I think it's easy to see that, facts that a model is trained on, even if you don't have access to those facts yourself, it's very easy to get those facts in the clear if you're allowed to issue queries. So, for example, there's this famous sentence, the quick brown fox jumps over the lazy dog. It's a cute example of a sentence which uses every letter in the alphabet at least once. Now, even if I don't know this sentence myself, I can just start with the prompt and I can figure out the rest of the sentence. So my basic question in this talk is very simple at a high level, which is, does being given API access to someone else's model provably make it easier for you to learn your own model, to build it? So of course, I'm a theorist and I just work on theoretical things. I try and prove theorems. And, there was a pretty big shock heard around the tech world, just a few months ago, which was when DeepSeek released R1. So this model sent shockwaves through the tech world because, in part, what they were able to do was able to achieve performance that's comparable to the O1 model, yet purportedly at a fraction of the cost. So all of a sudden, we had giant movements on the stock market. NVIDIA lost an unbelievable amount of money in their market capitalization. And really, the way that these things are trained is very much through model stealing and violating OpenAI's terms of service. So these problems have been fixed since then. But in the past, what happened was you could take DeepSeek R1 and you could ask it, "What model are you?" And it would tell you. I'm, ChatGPT, a model developed by OpenAI. Well, it's a very clear smoking gun that model stealing is apparently quite important and very important for a lot of these big tech companies, right? And ultimately in this ecosystem, when you have these kinds of, business models that are all predicated on the idea that I'm going to spend a giant amount of money training my model, and I'm going to allow you to access it. Well, if you can access it and reverse engineer parts of my model, maybe that changes, some of what you think about the valuation of these companies. So not much is known about model stealing in general from a theory perspective, really for this problem or for lots of other problems. And what I want to study is, are there algorithms with provable guarantees for stealing interesting families of language models? And I should mention the usual caveat that when you think about, modern language models, they have all kinds of bells and whistles that are very complicated and are very important for their practical performance. What I'm really going to ask is, are there simplified models that lead to, that allow us to study these kinds of questions and that lead to maybe new algorithmic insights on their own? So that'll be my goal in this talk. I should also mention a disclaimer. See, model stealing sounds evil and nefarious. I mean, it has the word stealing in it. There are non-nefarious reasons for doing this, which are very important in their own right. Maybe the most important of which is distillation. So, maybe I'm not trying to steal someone else's model, but I have my own giant model that's very expensive to store and deploy and perform inference on. And one of the things you might ask is, are there more compact versions of that model that I can learn through interactions with my own model that I've trained? That makes it easier to store, makes it cheaper to deploy, especially, at the end of the network, like if you want to deploy these things on your smartphone. All right, so what I'm going to do is I'm going to talk about model stealing for a very natural class of language models. In fact, I'll generalize it beyond this. So there's something that probably all of you have seen before, which is a hidden Markov model. So the way that a hidden Markov model works is it's basically a Markov chain. So there's some hidden state space S, and then you have a Markov chain that's making transitions within the space S. Now the catch is that you don't directly observe the hidden state at any time step. Instead, what you observe are observations, y sub I. And the crucial thing is that each observation y sub I only depends on the hidden state, if you knew the hidden state. So that's the crucial aspect of a hidden Markov model. In many senses, this is the original language model. This is a very simplified setting, but this actually goes back to Shannon's work already in the 1950s, where this was his simplified model of language. So there's another way that's useful to think about these things, which is in terms of their graphical representation. So here what happens is that I have these nodes that are going to be annotated with elements of my hidden state space. And then I have transition matrices, Rij, that describe, how one hidden state transitions to the next hidden state. And I also have observation matrices that describe the law of, if you tell me the hidden state, what's the distribution on observations at that time step? So these are the important matrices, the observation matrices and the transition matrices. And finally, to define this as a generative model, you also have to tell me the initial distribution on the hidden state. And that defines a process for generating sequences with very interesting types of dependencies. So let's start off with the basics, right? Hidden Markov models are a very natural generative model for sequential data. What's known about this very basic task of learning hidden Markov models? Let's say you don't know the parameters of your model, you don't know the transition matrices, the observation matrices, but someone allows you to get as many samples as you want from this distribution on observed sequences. What can you say about using that data to fit your own model? And it turns out that even though this question is very basic and it's a very simple generative model for sequential data, the answer is actually not as clean and nice as you would think. So if you want to know what you can do in terms of learning hidden Markov models, the answer is sometimes you can and sometimes you can't. So on the algorithmic side, there's a very nice paper of Mossel and Rock. It introduces a lot of tensor methods for these types of problems. That's a story for another day. But what they showed is that if the transition and observation matrices are all full rank, then there is a polynomial time algorithm for learning the model from random samples. So that's great, right? On the one hand, we know that under a natural algebraic condition on the parameters of the model, there are provable polynomial time algorithms. And yet, on the other side, we know that when these assumptions are violated, what happens if you have hidden Markov models where these matrices are not full rank? That actually shows up in quite a few contexts, especially where your hidden state space is larger than your observation space, which is a very common thing. Unfortunately, the trouble is that some of those hidden Markov models are genuinely computationally hard. So it turns out there's the standard assumption in cryptography, which is about the noisy parity problem. And it's believed that this problem is computationally hard. In fact, there are crypto schemes built on it. But the point is that you can build a hidden Markov model, which if you could actually find from random samples a model that agrees with it, then you would have actually solved the noisy parity learning problem. So this tells us that for this basic question, when can you learn hidden Markov models? Even this very simplified setting, the answer is sometimes yes, sometimes no. It depends on what assumptions you're allowing me to make about the underlying parameters. Yeah?
Full rank is not a very robust condition.
Yes, I agree. So in fact, you can sharpen these things. What really ends up happening, I don't want to go too far off track, but Noah, Dhruv, and I had some paper maybe 2 years ago which, gives a sort of softer version of this. It has to do with, how if you tell me the previous window of observations, the next observation you're given, can it still conditionally depend on previous observations that are way back in the past? So in a lot of cases, the window of your previous observations is a reasonable proxy for your current state. And when that's not the case, which is what happens with noisy parity, that's exactly what describes this dichotomy between where there are efficient algorithms and where there aren't. But maybe that's a topic for another day, but very good question. Okay, so I'm going to be ambitious. I'm going to ask, in this framework, right, where we're now allowed conditional queries to models, or we're allowed API access, does it remedy our computational woes? So where once we couldn't give such a clean answer, sometimes you can learn hidden Markov models, sometimes you can't. I'm going to ask the question, when you're allowing me query access, can I now all of a sudden learn all hidden Markov models? So that'll be my main topic for today. Okay, so let me define. Yeah,
The main difference is now you get to choose your query.
That's right. So ask me again after this. So let me be precise. What does API access mean here? So in the context of hidden Markov models, it's a very natural thing, right? Because it's really a generative model for sequences of observations, right? And so what you're allowed to do is you're allowed to specify a prefix of the trajectory. You tell me y1 is the first observation, y2 is the second observation, up to some threshold t, some time step t. And then, the true hidden Markov model would define a conditional distribution on how the rest of the trajectory is completed. That's what I'm allowing you to do, is you can specify any prefix you want, that's your query, and then what you get is a sample from the conditional distribution. How would the model that I want to replicate complete this prompt? So it's a very natural thing. And, I should mention that one of the other fun things about this model, it actually could have been studied a long time ago, but maybe there's some fresh reasons for coming back to it. It's related to a lot of classic results in learning theory. So back in the late 80s, early 90s, there was a lot of emphasis on, instead of just pack learning, where you're given passive access, from your distribution, you could instead ask, what if you're allowing me query access? There's a very famous result of Dana Engelin, who showed that you can learn all DFAs, all deterministic finite automata, under the uniform distribution if you allow me queries to the model instead of just passive samples. And so in a sense, learning hidden Markov models is a type of sweeping generalization of this old result of Engelin, because it's a more general model. Will be interesting. Yeah.
So does y1 to y2 have to be from sample?
No, you're allowed to specify any y1 up to yt you want, and there will be power in that, right? Because one of the difficulties really for hidden Markov models is the fact that when I see some interesting prefix, I'm not allowed to replay it and then go back and ask for another completion. So, that's exactly how we're going to try and find what are the interesting prefixes to ask about, but more on that later. All right. Any other questions? Okay.
Is it possible to specify a prefix that the generated model itself would never generate?
It is. Now let me table that for a second, because I have to tell you about what the learning goals are. Say doing it for something which the generative model would never generate isn't going to be useful towards my end algorithmic goal, but that is something you are allowed to do in this model of prison. All right. So in fact, I'm going to work with something even more general, and this goes back to a really nice paper, which I'll tell you more about. But it turns out that we can generalize hidden Markov models to something called low-rank language models. So here what I can do is I can take any language model, and I can think about organizing how it behaves. What are the completions it finds for a given prompt into a matrix, into a gigantic matrix, right? So every column represents all of the prompts you could ever ask about, all of the histories at time t. And then each row represents all of the possible futures of how it would complete. And this gigantic matrix, I can put in the entries in this matrix, whatever is the probability of the future given the history. So this is, just some hypothetical matrix that I could never hope to write down, but it's there. It's some defining characteristic of my model. And, the key definitional point is that we say that a language model is low rank if for every value of t, there is a good bound on the rank of this underlying matrix. So you should think about low rank as being polynomially bounded for this talk, okay? So as long as each of these matrices MT that I get has some polynomial bound on its rank, I'll be happy.
Polynomial in what? Variables?
Well, what I'll be interested in is there'll be a whole bunch of other parameters like the total trajectory length h. Maybe epsilon is my target accuracy, so I might care about things like 1/epsilon. Now we're going to end up with algorithms whose running time and sample complexity are polynomial in the rank bounds for the matrices. So really, as long as you have any reasonable bound, not a constant rank, but some reasonable bound, the algorithms will be interesting. So it's not, yeah, thanks. Okay. All right, so here's what I claim is that this is a generalization of, the thing we've already studied. So what I claim is that all hidden Markov models are low-rank language models. It's a very simple proof. It's a good way to make sure you wrap your head around the model. So why is this true? It's true because you can literally factorize the matrices, right? So you write down MT, that's this distribution on given each history, what's the probability of the given future. And I can explicitly write it out as the product of two matrices. One of these matrices, its column tells me the conditional probability given the history of what its hidden state is. That's an S-dimensional vector because there are only S possible values for the hidden state. And then I have this row vector that describes for each of the hidden states, what's the conditional distribution on the futures. So this is literally what a hidden Markov model means, is that it tells you explicitly that you can factorize this matrix. And you could hope, I'm getting ahead of myself, but you can hope that many natural language models, maybe they're not exactly low rank, but in some sense, maybe they should be approximately low rank. At the very least, this is an important structural property to investigate. Okay, so let me tell you about this beautiful paper that inspired us. So there's a very nice paper of Kakaday et al. So they introduced this problem of conditional query models for hidden Markov models and low-rank language models more generally. And they got pretty far. They got a polynomial time algorithm that works under some condition called high fidelity. Now, high fidelity, I've read this paper a few times, very hard to define. I'm not going to define it. It's kind of a pain in the butt. So let's just skip it. Yeah.
Were there any empirical evaluations of existing things?
Let's get to that later. Why do you guys keep asking questions that are later? All right. So it requires a bunch of background. I'm not going to do it. Huh? All right. You're fired. All right. So it takes a bunch of work to define high fidelity. Essentially what it is it's some kind of spectral well-behavedness of bases. I'm going to have to explain what bases are in general later, but let me not go here. Let's just say that this is an interesting paper that doesn't quite get all the way there. But here's a kind of fun result just from a couple months ago. What I claim is that there's a polytime algorithm for learning any hidden Markov model or low-rank language model from conditional queries. So those computational lower bounds we had for noisy parity, those are not there, and there's nothing. You can learn everything. So let me be more precise with the theorem statement. Okay, so you can take any language model. Let's say it has alphabet size A. It's got horizon at most h, so it generates sequences that are at most length h. Let's say the rank of each of these matrices MT is at most some parameter S, right? That's the complexity of my model. Then what I claim is that there's an algorithm that makes at most Paulian A, H, S, 1/epsilon, queries to the model. Epsilon is my target accuracy. And what it spits out is a description of a model that can generate sequential data that is efficient. So you can efficiently sample from this model. And it has the promise that it's epsilon close to the true language model in total variation distance. So this is, about as strong as you could hope for such a set. Okay, and let me tell you about some of the main ideas. In fact, there's something kind of funny that happens here. See, a lot of times in learning theory, it's kind of obvious that there is some inefficient algorithm, like if I allow myself brute force search. For hidden Markov models, it's obvious that there is some inefficient algorithm that takes polysample complexity. For low rank language models, it's actually not obvious. So something funny is already happening here, right? So what if I tell you that the rank of all of these matrices MT is bounded by some parameter, right? See, the trouble is that the matrices, they all have exponentially many rows and columns. Like think about literally just one of these matrices, MT. It's got a row for all possible futures. It's got a column for all possible histories. This is, exponential in every sense of the word. So what if I tell you the rank of this matrix is at most 10? Why does this matrix, why can it be described by a polynomial number of parameters? That's not at all obvious. In fact, if you told me just one single matrix that was low rank but was exponentially large, it really would have exponentially many parameters. Right? So this problem is not at all obvious why these kinds of things should be solvable with a polynomial number of samples, period. Now, the key for this is really that, why it's possible to describe a low rank language model with a polynomial number of parameters. This intrinsically has to do with the relationship between the MTs. Otherwise, it would just be false. So that's the first thing I want to do is I want to explain what is a reparameterization of low rank language models, which makes it clear that at least if I ignore the algorithmic and statistical complexities, that in principle, I can perfectly describe it with polynomial description complexity. That's not obvious, and that I have to explain.
The previous slide has put also the polynomial in A and H.
Yeah, that's right. Yeah. Okay, so let's work towards goal number 1. I'm going to tell you why there's a succinct representation. And the fun thing is I get to tell you about a lot of, beautiful and important tools that show up in a lot of online learning. Here we're going to use them in a different way. But there's this tool that if you haven't seen before, it's beautiful. Okay, it's called the barycenter expander. So in a lot of applications in learning, you're faced with this problem that you're given some set of vectors, and you want to somehow find a representative set of those vectors. Okay. And the way that you should think about this mapping onto our problem is that, our set of vectors will be the columns of MT. Those are all of the possible distributions on futures for any given history. And what I want is I want some representative set of histories. At the end of the day, the main difficulty in the problem I'm telling you about is I'm allowed to query whatever histories I want and get conditional samples. I can estimate those distributions. But in what sense can I then estimate other histories I haven't seen before, right? So I want some representative set that when I know what their distribution on futures looks like, that allows me to extrapolate other things. Now, these vectors have exponentially large dimension, but they all live in some S-dimensional space. That's the assumption of being low rank, so that'll be critical here. And now, instead of like in an ordinary linear algebra class, you would just talk about like what's a span for the set, what's a basis. Bases are not very good because at the end of the day, if I have some basis, x1 up to xs that spans my space, the trouble is that even if I use conditional queries to very accurately estimate each of these xi's, then when I try to, bootstrap my estimate of x, I'm going to blow up my estimation error by whatever are these coefficients. So barycenter expanders are the slight twist that almost sounds too good to be true. Instead of looking for an arbitrary basis, x1 to xs of your space, you look for one in which for every other vector x in your set, it has the property that there exists a linear combination of the generators and that those coefficients are bounded by some constant c in absolute value. So it's a stronger constraint than just spanning.
You actually need it to be a basis. If it's slightly larger than a basis, you still get.
If it's not a basis, yeah, you're going to have trouble because if these sets really do span, okay.
Like slightly larger than a basis.
Yeah. Let's yeah. These are details. So one of the things which is maybe not obvious is this sounds like a great definition. It's actually not obvious the first time you see it. Why should C approximate barycenter expanders exist? Right. There's a beautiful result due to Auerbach and Kleinberg that for any C at least one, they do exist. And the proof for this isn't even hard. Basically, what happens is you start off with some basis for your space that spans. And whenever there's a violator X that cannot be represented with bounded coefficients, what it means is you can do a swap. You can swap X for one of the Xi's in such a way that the determinant becomes larger. So as long as the determinant achieves some maximum value because your space is compact, it exists. But even better, as long as you can optimize linear functions over your set omega, it doesn't even need to be convex, then there is an efficient algorithm for constructing these barycentric spans. So this is tool one. That's very powerful.
Quick question.
Yeah.
Is this here a universal constant or does it depend on the dimensions?
It does not depend on the dimension. So what's really cool about it is that C at least one, it exists, which is really neat. Now there's a slight gap that only when C is strictly larger than one, do you actually get efficient algorithms conditional on an optimization oracle. But that's an interesting question maybe for another time. Okay. All right, so there are tons of applications in online learning and RL. And now what I claim is that barycentric spanners give you a way to parameterize low-rank language models so that they have a polynomial description. So let's do that. Okay. So here's the blueprint. This is going to ignore all algorithmic and statistical issues, but it's actually pretty simple. So the way that we're going to reparameterize language models is we're going to construct a barycentric spanner for each of these sets of vectors, the columns of MT. Fine. I'll have to tell you later how we do that, and that's a whole other can of worms. Now, as I'll explain, the main trouble is what do you do with these barycentric spanners? The point is that a barycentric spanner gives you a way of expressing X in terms of the other things you have. But what is that linear dependence? How exactly do you compute it? And how do you track how these things evolve? So the point is, like, what if someone gave us the barycentric spanner? We know that they exist. You take any MT, you take their columns, and then there exists a one approximate barycentric spanner. These are, H1 super T through HS super T. And now just to belabor the point, right? So if I want to use these barycentric spanners to predict the distribution on futures or the distribution on next tokens, now I have to deal with this problem that you give me an arbitrary history X. That induces some conditional distribution on futures. That's what I want. Because in order to define an efficient sampling procedure, I have to know what comes next after X, right? And I know by the properties of barycentric spanners that there exists coefficients, lambda I super T of X, that give me the right way to add up the vectors for the histories in my barycentric spanner. The trouble is really the fact that these coefficients depend on X, right? As you change X, they change in a pretty crazy way. And so in principle, I need to know what those coefficients are in order to use my barycentric spanner. So what I claim is that you can actually track how the coefficients evolve sequentially. So what if you gave me the coefficients, the lambda i's at some time step t? How can I sample from the correct conditional distribution, on the next token? So the point is that, let's say I got the next token as O. So now my history becomes not X, but X appended with O, right? And what I care about is what are these new coefficients? I have a new set of barycentric spanners because this is happening on MT plus 1. So where do these coefficients come from? And this turns out to actually be pretty simple. I claim you can use, essentially elementary probability theory to compute what exactly those coefficients are. And it has to do with the relationship between MT and MT plus 1. So the point is that if you take any future whose T plus first token is actually O, then I claim that the probability of F given X is the same thing as the probability of F given X and O. O is the agreement portion times the probability of O given X. This is just, a very simple, conditional probability computation. But if you take this in mind, if I take my old expression, the probability of F given X is expressed this way, and I know the lambda I sub X's, right? Then the point is that, now what I can do is I can plug in this expression, right? And I'll get, this slight modification, right? Where now I've, added O to my trajectory. And now I can rearrange things And what I get is a very simple expression. If you tell me the lambda i's, well, as long as I know the probability of the next token given each of the elements of my barycentric spanner, and then I can hope to try and update it, the coefficients. Now the twist here is that this is really describing things in terms of the new distribution on futures. It's described in terms of a linear combination of the distribution on futures as I grow out the histories. But the point is that what I really care about are the histories that serve as the barycentric spanner at time t+1. So what I should really do is express each of these in terms of the basis at t+1, and that's just a change of basis. So once you use Bayes' rule and a change of basis, you're golden. Right? This gives you exactly what you want. And then from these coefficients, you can just very simply compute what the next token probabilities are by aggregating over all the futures that start off with that observation. So the main point is that this is the idealized blueprint. It's not obvious there's a polynomial-sized description of low-rank language models, but barycentric spanners give you the key. Once you have barycentric spanners, you can describe a way to track how the representation changes just by writing down an appropriate change of basis. And that gives us our first goal, right? But now we have to solve all of these, main challenges in getting this sort of blueprint off the ground. All of this was, very optimistic. Where do my barycentric spanners come from, right? And, there's actually a more nasty issue than just that. And it turns out there's this really nasty issue, which has to do with how the coefficients blow up. As I'll explain, if you do it in a naive way, then the coefficients, any estimation error that you induce at each step, it can blow up exponentially with the horizon length. That's actually where the coolest new idea is. So my goal for the rest of the talk is really just to tell you two new ideas. Okay, we're going to solve both of these problems. So let me tell you about the first part. How exactly can you construct these barycentric spanners? Because they're all happening in this very inaccessible space because they're happening on exponentially long vectors. So here is a very simple idea that we can borrow from sketching, right? Which is that maybe I have these vectors implicitly that are exponentially large dimension. Can I create some kind of representative vectors that are much smaller dimension that act as an effective surrogate? Any operation I want to do on the true vectors that helps me construct the barycentric spanner, I hope that I can do on the surrogates instead, right? And here it's just the definition. So imagine you give me a fixed set of histories that I care about. They each have their vectors, which are columns and empty. And maybe for each one of them, there's some clever way of constructing a vector v sub h that depends on the history, but it has this nice approximation property that for linear combinations of the v sub h's with bounded coefficients, that the L1 norm is very close to what the L1 norm would be if I operated on the full dimensional vectors instead. See, what this means is that, an approximate barycentric spanner for one set of vectors is automatically an approximate barycentric spanner for another. Because what does a barycentric spanner mean? It means I take one x and I can express it almost exactly as a linear combination with bounded coefficients. The error in the approximation is just some appropriate L1 norm of some bounded linear combination. So this is really the thing I need in order for them to be an effective surrogate. This is just the definition. And now the point is actually very simple, right? So imagine I some way, somehow construct the distribution D, which is a distribution on futures. And now what I can do is if you give me some history H, what I can do is I can try and sketch some estimate of its true gigantic dimensional vector. What I do is I sample futures from this distribution D, and then I look at the probability of F given H, and I renormalize by M and the corresponding probability of this distribution. So these are very standard estimators, but the point is that now these actually give me unbiased estimators for L1 norms. Because if I look at things like the expectation of some coefficient of V sub H, I've got a DH in the denominator and I multiply by D of F1, because that's the probability that D generates. So if you work out the details, then the point is that this in expectation reserves L1 norms exactly. And the entire point is that you can choose a good distribution that has the property that this unbiased estimator has bounded variation. So hence you get concentration too over all bounded linear combinations. And finally, this really gives you a procedure if you have a small number of histories. For each one, you can write down a V sub h. Ultimately, what you do is you subsample the histories according to your generative model. And the point is that as long as you cover the typical histories of your barycentric spanner, you will cover a large fraction of the actual space of your distribution. So the crux is really that, sketching is kind of a useful way to do dimensionality reduction to construct the barycentric spanners. But I want to tell you my favorite part of this, which somehow is not a priori where you think the main challenge is, but this is really the heart of the issue. And there's something cool that, is a simple takeaway. It's very nice here. So let's say we could do all this. I can sketch so that I construct approximate barycentric spanners. At the end of the day, in this idealized blueprint, what I told you was that there's a way of estimating how the coefficients change. Now, I gave you an exact algorithm because you do it through some change of basis and some Bayes rule. But ultimately, if I try to make that blueprint work now when I'm given random samples, I'm going to have sampling noise. That's life, right? So the issue is that I'm never getting the lambda i's, the things I want. I'm only getting some approximation to it. I can take, as many samples from my conditional sampling oracle as I want. I can get finer and finer approximations to it, but there's always some error. Now, something very funny happens, which is that I claim that this estimation error, if you do it naively, can blow up exponentially with the horizon length. And let me show you, why that is. See, the issue is that even if I've computed the barycentric spanner, right, I know that the true coefficients are bounded by at most 1 in absolute value. But now when I add sampling noise, who's to say that the coefficients, my estimates, are actually bounded in absolute value by at most 1? The sampling error could have actually blown up the norm, right? So the point is that really, if you want to abstract it, we could look at, there's a true vector, which is the distribution on actual futures given the history x. And then I have the space of things that I generate from my barycentric span. That's a nice convex set. It's really just, I take all of the future distributions for the elements of my barycentric spanner. I look at all the distributions that can be realized as bounded linear combinations of them. But the trouble is that, even though we know that this vector z is in the set script k, our estimate is not necessarily in the set script k. Our estimate is when I take my estimates of the mixing coefficients and create my own, estimate of the future vector. So the issue is that, what I would have liked is, you just naively get back into the set. I know that z is in the set k, and what I'm given is w by my algorithm. So what I could try and do is, given w, I can try and select out some element, z prime of k. And I would ideally like the property that that doesn't blow up the error, right? Whatever your L1 error was, between your estimate, w, and the true vector, z, that's my statistical error. I want that now when I map w to some other point, z prime, in the set k, that I haven't increased the statistical error. So the first time you see this is very natural because usually projection doesn't increase the distance to other points. Unfortunately, there's a big problem with this. Anyone have any objections? It's false. Yeah, that's not so good. It turns out that it's impossible. So if you select the point based on an L1 projection, you look for the closest point in L1, it's false. You lose a factor of 2 by the triangle inequality. In fact, it's not just false for L1 projection. You can show that any mechanism for selecting out a point in the convex set actually is doomed to lose some constant larger than 1. So this is a deal breaker because this constant would mean that you end up blowing up your error at each time step. And that would be terrible. You would end up with not polytime algorithms, but exponential and H algorithms. It turns out there's a very simple fix, which is just use KL divergence instead. So there's a standard fact, which is that, if I look at the projection according to the KL divergence, then I actually do have the inequality I want. That, the KL from the truth to my estimate is an upper bound from the KL divergence of the truth to my smooth estimate, my denoised estimate. And what this means is that all of those things I told you about, approximating the barycentric spanner, you just have to do them in some version that's friendly to these kinds of projections. So what you have to do is use basically some kind of truncated version of KL divergence. That's basically how the algorithm works, is preserving truncated KL. So that was the main, technical points I want to get. I wanted to have as my takeaways. Let me try and speak to the experimental questions. That's always a difficult thing. In life, all of us are trying to figure out what is the use of theory in modern language models. I don't have any amazing answers, but I do think that sometimes a lot of these theories, theoretical investigations, they allow us to think about different kinds of questions than you'd ask before. So now let me finally come to Raghu's question. One of the things you could ask is, structurally, is low rank a reasonable model, or is approximate low rank a reasonable model? It turns out that there is a sense in which it's approximately true. So you can do the following experiment. We did this on this tiny stories language model. So you take 10,000 samples, you take a random history HI just from your generative model, maybe with given some prompt, and then given HI, you generate a random future. And each of these are 32 token length. And now what I'm going to do is I'm going to create an induced matrix on the MTs. I'm only going to look at those columns for the histories and those rows for the futures. Now there's a slight twist, which is it turns out that we don't actually use the entries of the matrix. Instead, what you do is you use the log of the probabilities. A lot of times you need that kind of smoothing to get this. But then you actually do have a very sharp decay in the singular values, which is really cool. So even though the matrix is gigantic, this future by history matrix, it's not as large as the true one, it's still an induced matrix. It turns out that there are very, very good approximations that are much smaller ranked than this. So one of the things that I find really interesting and worth exploring is, once you know that these kinds of structures are maybe somewhat to be expected in language models, what can you do with them? See, originally I set up the goal as let me steal a language model that's epsilon close in TV. That's maybe, it's not that that's going to be the first application that you expect for these techniques, but let me ask a different question. So what does this kind of approximate low rank structure mean? In some sense, it means that, there are some representative histories so that other histories that are not in the set, you can express their distribution on futures as a linear combination of what happens in your representative set. So this maybe now starts to remind you of things like word embeddings, which give some way of organizing the space in some kind of linear way that you can solve analogies. One of the questions I wonder is, computing barycentric spanners of these columns of MT, what can you do with it? Is there a sense in which you can solve interesting NLP tasks? Does it give you a more interpretable way to think about what are all the possible answers of the language model? I think there's a lot of cool questions here to explore, but let me just wrap up for now and tell you what I hope you got out of the talk. So what I did was I introduced you to this beautiful model of Kakade et al., where you study conditional queries, and that allows you to get around the computational lower bounds of learning hidden Markov models and learning low rank models. What I showed you was that you can actually learn all hidden Markov models and all low rank models this way, just through a very simple scheme. I gave you new techniques which are based on constructing barycentric spanners. Really, you're constructing barycentric spanners on implicitly defined vectors as long as you're allowed sample access of the corresponding distributions. And maybe most excitingly, I showed you how there are ways that tame how the error builds up over time. Instead of just doing things like L1 or L2 projection, that's where high fidelity came in as an assumption. Those are usually computationally very easy things to do. The point was that here I was allowing myself to do more work as I'm doing the generative model because I'm doing projections and KL divergence. And this allows you to actually tame the way the error blows up. So this also seems like an interesting facet of it. But let me stop there and, thanks for your attention. I'm happy to take any questions.
Time for a couple of questions.
Thanks, Kurt. Yeah, the low rank language model reminds me of low rank MVP and
Yeah.
Getting could you comment on the connections there and the techniques used and whether your result imply anything over there?
Okay, we were inspired by that. Also this same thing happens for low rank MVPs. where, whether or not that's a reasonable structural assumption, a lot of times it's much more reasonable when you have the log probabilities instead, which is exactly what we're studying here. Beyond that, I don't know more. It's a very powerful analogy, but what should I do with this? Your guess is as good as mine. I think it's exciting, but I'd love to discuss more. Yeah. Yeah.
So these histories that you're querying, do you, like, is it pre-computed or do you?
It's not pre-computed, yeah, we updated. So the point is that, I went over a bit fast on this part, but the point is that when I had these representative vectors, it was really a procedure given a history for computing its representative vector. Now the question is, what histories? So the main point is that if you focus on a time step t, and I just hit the button and generate a ton of histories for that time step, then, it's not that among that set of histories you observe, there's always going to be a very centric spanner, because there could be some vector that's very rare that you just don't cover. But the point is that, with high probability, you're going to have an approximate barycentric spanner among the random histories you've seen. And you can throw away that epsilon part because it gets eaten in the feed. So basically, the histories we query are, you basically query it randomly to find, a large enough cover statistically for the distribution. And then you know that a barycentric spanner is somewhere in that set. And that's where the representative vectors come.
Would you like design these histories as you go along?
You could. I mean, one of the other things, like I find, the experiment is really interesting. We're just working on it now. I also wonder, like, it reminds me also of, there were these things people were very excited about some time ago called determinant point processes. And there the idea was that instead of just retrieving the best responses to a given query, you might try to recover some notion of diverse answers. And so once you have this linear algebraic structure, you can talk about what are different kinds of completions of the history. And maybe instead of just resampling the model as many times as I want, maybe this gives me a better way to understand what are the space of possible futures or answers. So there are a lot of cool questions, but I have no, real idea here.
So let's save remaining questions for the break. We're gonna have a 15-minute break now, and let's hang for 2 to 3 minutes.